Hi everyone, today I'm gonna teach you how to know if any overflow is going to occur or if you have any overflow after adding two numbers. We have 5 cases for the addition, and starting with the first one, adding two positive numbers. When you are adding two positive numbers, you may have an overflow or you might not, based on some conditions. If the sum of the two numbers were less than 2 power n minus 1, so you will not get any overflow. What do we mean by n? N here is the number of bits. So for example, if you are adding two binary numbers, each one consists of 4 bits, so here n will be 4, so 2 power 4 minus 1, you will get 2 power 3. 2 power 3 is 8, so in this case the sum shouldn't be greater than 8, or if the sum is less than 8, you won't have an overflow. And here we have an example. We're adding 3 plus 4, and we're using 4 bits to represent each number in binary. So 3 in binary system is 0, 0, 1, 1 using 4 bits. As you know, previously we explained how to convert from decimal to binary. So here we have the 4 bits starting with 2 power 0, and each time you increment the power, these two we fill them with 0, and the bits that are filled with 1, if you add the values of them, you will get 3, because this one 2 power 1 is 2, 2 power 0 is 1, 2 plus 1 is 3. And also you do the same for 4, so it's 0, 1, 0, 0. And you take these binary numbers, you add them together, and now I'm gonna tell you how can you add two binary numbers together. So 0, 0, 1, 1 plus 0, 1, 0, 0. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. So here's our binary number, and as you can see that this number is equivalent to 7 in decimal system. So 3 also plus 4 is equal to 7, so the answer is correct. And as you're adding two binary numbers together, these numbers are still positive numbers, as you can see, so we didn't get any overflow, and also 7 is less than 8, so the answer is correct. Moving to the second case, if you're adding two positive numbers, but in this case the sum is greater than 2 power n minus 1. Also, all the examples that we're going to go through now, we're going to deal with binary numbers, which consist of 4 bits. So also here, for this case, the sum will be greater than 8. So if the sum is greater than this number, an overflow will occur and the result will be wrong. Also, like the overflow only happen when you're adding two numbers with the same sign. For example, if you're adding two positive numbers with the same sign, if you got like negative signs, so you have an overflow. Or if you're adding two negative numbers together and then you got a positive number, so in this case you have an overflow. Or you're adding two numbers and then the number of bits is less than, or you can't actually represent this number using this number of bits, you need extra bits, so you'll have an overflow in this case. So now we're adding two numbers, and in this case, and in this example, we're accepting to get an overflow. We're using 4 bits to represent 5 and 6, so the equivalent number of 5 in binary is 0, 1, 0, 1 using 4 bits, and for 6 is 0, 1, 1, 0. We're going to add these numbers together, so 1 plus 0 is 1, and 0 plus 1 is 1. 1 plus 1 is 0, and here we have carry. This carry, we're going to add 1 plus 0 plus 0, you get 1. So actually, as you can see here, this bit was for this sign. It's the sign bit, and we had like two positive numbers, and then here the sign bit has changed. And also the answer of these 5 plus 6 is 11, and as you can see that 11 is greater than 8. So here we got a wrong answer. It requires more bits to represent 11, and we have an overflow. Moving to the third case here. In this case, we're adding two numbers with different signs, positive and negative number. Actually, in this case, you don't get like it's rare to get an overflow when you're adding two numbers with different signs. So now we're going to go through the examples, and you will see how you actually in the two examples you're not going to get an overflow, because as I said previously that the overflow actually occurs when you're adding two numbers with same sign, or and then you get a different sign, or it requires more bits to represent the number. So here we have 5 and negative 6. In this case, we're not going to subtract 5 from negative 6. We're going to add them, and to avoid the subtraction in binary numbers, like when dealing with subtraction with binary numbers, we're going to add 2's complement. That's why it was important really to know how can you represent binary negative numbers in binary system using 2's complement. So let's convert these to binary system, from decimal to binary system. 5 is 0 1 0 1, so here our 5 is ready. And 6 first, negative 6 first, like before representing negative 6 we're going to take 6, and 6 is equivalent to 0 1 1 0. Then we're going to find the 1's complement of 6. So as I told you previously that 1's complement and 2's complement are representation of negative numbers in binary system. So we're representing actually negative 6. So we're going to change every 0 to 1 and vice versa. So this one will be like that. Here is our 1's complement. And to find the 2's complement, just add 1 to 1's complement. So 1 plus 1 is 0, and we have here carry, and then 1 plus 0, then 0 1. So here's our 2's complement for 6. And you take the 2's complement and your number, add them together. 0 1 0 1 plus 0 1 0 1. So now we will get 1 1 1 1. And actually this answer is correct, because 5 plus negative 6 is negative 1. And to double check, negative 1 actually is less than first, yes, negative 1, you can know how is your, like, you can know if your answer is correct or not by finding the 2's complement for 1 and compare the answers. So how can we represent 1 using 4 bits? In binary, it's 0 0 0 1. Then here is our 1's complement, and for the 2's complement you will add 1, so 1 1 1. This is the 2's complement for 1. So the answer is correct, they are the same. Moving to the second example, but for this time and for this example, the magnitude of the positive number is greater than the magnitude of the negative number. So 6 is greater than 5. So we're accepting to get a positive number. 6 in binary is 0 1 1 0 using 4 bits, and negative 5 is first 5 is 0 1 0 1, and for the ones complement it's 1 0 1 0. Add 1 for the ones complement to get your twos complement. So here's our twos complement for 5, and then we have 0 1 0, 0 1 1 0 plus 1 0 1 1. You will get 1, then 1 plus 1 is 0, and we have carry, and here it will be 0, and we have another carry, and here 0, and here we have a carry. For this part, just ignore the carry, and you will find that you got 1 in, which is the right answer, because 6 plus minus 5 is 1, and this is the representation of 1 in binary system using 4 bits. So it's a correct answer. You ignore the carry, there is no overflow. For the fourth case, we have two negative numbers. We're adding them together, and we are checking the sum. Actually, in this part, to check if the number is greater than or less than 2 power n minus 1, you take the absolute value of the number, because when adding two negative numbers together, definitely you'll get a negative number. So to compare the results, we take the absolute value of the number and compare them, or taking the magnitude and ignoring the sign, to know if the number is greater than or equal. Actually, this one is the same. If the number is less than 8, also we're going to deal with 4 bits, so let me write it like that. 2 per 3, which is 8. So except we're here expecting to get a number which is less than 8 as an absolute value. So we have here -3 and -4. In this case, both of the numbers, we're going to convert them to binary and then find the twos complement for -3 and -4 as well. Let's start with -3. So 3 in binary is 0 0 1 1 using 4 bits, and then to find the ones complement is 1 1 0 0, flipping the ones to zeros and vice versa. Then you add 1 for the ones complement to get the twos complement. So here's our twos complement for 3. And for -4, it's 0 1 0 0, then ones complement 1 0 1 1. For the twos complement, it will be 1 0 1 1 plus 1. You'll get 0 and carry, and then 0 and carry, and then 1 1. Going to add these together, and let's see. Plus 1 1 0 0. For this one, you will have 1 and then 0, and then you have 0 and carry, and then 1, and here you will have 1. So this answer, -3 plus -4, will give us -6. So actually this number, if we took the absolute value of it, is less than 8, and so there is no overflow. And also you can double check, if you ignore this carry, there is no overflow, and you will have you can find the twos complement for -7. You will get the same answer, and if you got the same answer, so the answer is correct. So let's just do it now. 7 is 0 1 1 1 using 4 bits in binary. Then the ones complement is that. This is the ones complement for 7. We add 1 for the ones complement. You will get 1 1 1 0 0 1. So here's our twos complement, and they are the same when ignoring the carry. So the answer is correct. There is no overflow. For the last case, adding two negative numbers, and then the sum, the absolute value of the sum is greater than this number. In this case, we'll have an overflow. because actually we need like an extra bit to represent the number, and also you'll see that like minimum we need 5 bits to represent the number that we're going to get. Of course we're going to have these two numbers in two's complement form, so let's just convert them now. -5 and -6. 5 in binary is 0 1 0 1, then 1's complement, then we add 1. Here is our 2's complement, and for -6, 0 1 0 0 1 1 0, then 1's complement, add 1. 1 plus 1 is 0, and we have the carry, then 1, then 0, and then 1. So this is the 1's complement, this is the 2's complement for -6, and for -5 also. We're going to add them together. 0, and here 0, and then, so as you can see here we have a different sign, and here we have a carry. We can't actually represent -11 using only 5 bits. Minimum, like it requires 5 bits actually. So here we have an overflow, and the answer is wrong. And I just would like to mention that these examples are taken from Fundamentals of Logic Design. And this is the end of the video. Thanks for watching.